Alright chat, this is day 17 of building a computer in Minecraft. Let's go! So this is the world that I was in, that I'm still in, and literally every single design here is my own. Nothing from the internet, no schematic downloads, no circuit diagrams lookup. Everything is my own, and that's what makes this so much more satisfying. So here's the agenda for today. You can see the whiteboard, let me actually hide it so that I can show you the stuff in the world. So here I have this 4-bit ALU. It can do addition, subtraction, comparison, negative numbers. It can also do multiplication if you do addition multiple times. So you can use the software to emulate multiplication. I'm pretty sure you can also try doing division on it, but it's gonna be a little difficult. Here is the 16-bit ALU. I've literally stacked this 4 times, so this does have a tad bit of delay, but well, I can't really complain. And then over here I have, this is the 4-bit ALU, except this has the flags up top. These 2 flags, so you can use this for the logical comparisons. You can use it to see if the number is negative or positive. This one doesn't have the flags, but it is a part of an ALU, the major part of an ALU. So why am I showing you this? Because today it's finally time to compile the computer. Use the ALU, use the program counter somewhere over there, use the memory modules over there, the display over there, and then just combine it into a massive computer. At least that's the plan. We'll see what happens. Let me show you the RAM modules as well. This is a 256-bit RAM module, so you can store 256 bits of data into it. That's cool, right? And then here's some prototypes for the display. Another one over here, I think. Yep, look at how many displays we have here. Hold on. So the last one is the final working iteration of the display. Let me show it to you. Oh wow, that was closer than I expected. But yeah, so this is a working display, and I'm not really writing anything to the display right now. It's just displaying the randomness that happened to be saved in it while I was creating the thingy. But well, I should be able to write stuff to it, and it should display it without much error. As you can see, it's not really very good at saving its contents, but I don't know, it should be fine, I think. I have no idea why the values of these registers change for absolutely no reason. But yeah, I don't know what else to say. I tried neo jumping. I'm still just as bad as I was 3 years ago. Just one neo jump. Yes! Anyways. So here's the agenda for today. Let me try and figure out the arrangement for the computer architecture. I've created all the designs, so I just have to figure out a way on how to connect them all up. So hopefully the whiteboard should be visible. You should be able to see me scrolling through it. So yeah, I've gone ahead and made some notes. Let me actually grab my pencil. Yeah. Okay. You can ignore this. Assembly language is not this title. So yeah, the registers in the CPU. Here's what I haven't discussed yet. So the CPU, how does it actually do compute? You see that ALU over there? Let me fly to it. The arithmetic logic unit. It has 2 inputs for numbers, right? You can give it 2 numbers. Which 2 numbers will you give it? Will you just give it 1 plus 1? You can give it numbers manually, and then it acts like a calculator. But a computer should know which numbers to add. So it should have registers. One register here, another over there. This one connects essentially like a temporary variable. Like when programming, you create temporary variables, right? How many of y'all are coders? Tell me in the chat. So let's say you are doing 5 plus 7, which is an intermediate calculation. So you can store it into D. You can also use D like an incremental variable. Let's say you have to increment it by 3. So you can do D equal to D plus 3. So that increments D by 3. And yeah, that's literally it. The D register is quite simple. And then you have the... Let me actually keep this open. So yeah, then we have the A register. And the A register is a little more complex than the D register. But you should be able to understand it if you've tuned in for much of the series. So, this is the address register. And it stores the address obviously. But it can also store regular data. So right now think of it like a regular register, like the D register itself, except it has a side effect. So you can use it to store any sort of data, except whatever you store in it also goes to the RAM module. So as you can see, the RAM module has some inputs. Some of them are the address inputs. 1, 2, 3, these 3 are the address inputs, these 3 are also the address inputs. So yeah, whatever you give to the address register, that also gets fed into the RAM. So you're essentially selecting a register when you write some value to the A register. Now it's up to you if you use the value coming from the RAM or you choose to ignore it. Either way, that's completely fine. And then you have the... Yeah, and then... Oh yeah, let me mention this important section over here. So what you see here, @A100, when writing a code, this is the syntax that you're gonna follow to write something to the A register. Generally, you can't do A equal to 3, that's probably not how it works. I mean, you could make it work, but... well, not here. So then we have the third type of register, the M register. And this register isn't physically present inside the CPU, but rather it's a pseudo register. So for the sake of programming, you're gonna assume that it is a register, even though it's in reality more like an input. So you have the RAM, and whatever is the output of the RAM, you connect it to the CPU, and that acts like the M register. So when you are programming, you can use whatever is in the M register, the pseudo M register. Whatever you read from the M register is actually what's coming from the RAM. So you're essentially reading the RAM through the M register. And yeah, it's not a register. It's not a register, as I said, but it's in the mischievous music. Anyways. So yeah, next let's discuss the instruction. Oh, hold on. Oops, what? Did I go to the previous song by mistake? So, now that we have the registers discussed, let's go to the instruction over here. And you know, you write code like, if you write code like 1 plus 1 equal to whatever, A equal to 3 plus 3, let's say that's a valid piece of code that you write. Over here, we are gonna be giving instructions in binary, of course. So let me show you. This is a 16-bit instruction. And okay, I'm gonna be completely honest here, full discretion. Some parts of the assembly language are not my own. Yeah, I'm not blatantly copying it. Obviously, I'm understanding everything and using my brain everywhere, literally. But yeah, I mean, I'm more of a hardware person than a coding person, so I frankly do not know how an assembly language works. But yeah, I'm taking some inspiration, but I'm gonna do my very best to explain everything. And it does make complete sense. It's also very elegant, honestly, so... Anyways, let me explain the instruction. As I said, this is 16 bits. The first bit means that the following is actually a value for the A register. So if this bit is 1, then all of this is what we are gonna save into the A register. So yeah, this works like an @ symbol. If it's 1, then it means that we are writing stuff to the A register. Otherwise, it's just a regular instruction. So then these two actually don't have any purpose. All they do is that when we are writing something to the A register, then they can have some value. Otherwise, you just ignore them. And then here, we have this purple bit. And what that does, actually before that, let me explain the inputs that will actually be connected to the ALU. Let me use the 16-bit ALU right now because it looks more tasty. This will be the D input, D register. The D register will be connected to these inputs, and then this will be the A/M register. So now you're wondering what's the A/M register. There's an A register and an M register, but what's A/M? Let me tell you. So if this bit over here is 1, then this input will be M. But if this bit is 0, then A will be selected. So by default, you are selecting A register into the second input. And if you select it to 1, then the M register, which is actually the register selected in that RAM module at A position. So yeah, either the value in the A register or the value in the RAM at A position. I hope that makes sense. And then the rest 6 of these feed directly into the ALU. So these 6 levers you see here, 1, 2, 3, 4, 5, 6. These 6 levers are literally these 6 bits over here. That's how simple it is. So you can use these to do addition, subtraction, comparison. Yeah, you can. These levels are actually genuinely overpowered. Let me show you how you can write 0. So there's literally an input for zeroing everything. You don't have to negate it. 0 this. You can AND it, I don't know, doesn't matter. There you go. Everything is 0. If you wanna make everything 1, you can negate this one as well, and yeah, you can AND them because AND is faster actually. That's probably the only reason. When you want to add them, then it ripples. So yeah, that's slower. Oh yeah, if you want the ALU to output 1, this is how you're gonna do it. Add all ones with all ones, you get this bit 0, the rest of them ones, then you negate it. Look at how elegant this is. You usually don't see stuff this elegant. Oh, hold on, all the inputs are 1, that's interesting. So yeah, this is the elegance of this. Let me show you how you can negate an input. So let's say you want to output -D, okay? So this is D, whatever you're inputting into it. Let's see what you're inputting. Just 3, okay, whatever. So you're inputting just 3. I believe, oh yeah, when you're gonna negate this, it's gonna use kind of 2's complements logic. It's gonna give -D -1 because you're not adding 1 to it, right? So it doesn't properly transform it into the negative. And then you're gonna go ahead and 0 all of this. You don't need this input, it does not matter. And then what if... Yeah, so for minus d, oh yeah, you just have to add 1 to it somehow. If you add all ones, that's minus 1. So you're doing minus d minus 2. If you add all of them, then that's gonna do... Yeah, that's gonna do minus d minus 2. And then you negate all of it, so it does d... so it does plus d plus 2 minus 1. So that's d plus 1. Well, yeah, anyway, so you can see that this is incredibly powerful. I'm just gonna turn off all of these. And yeah, let's continue with the rest of the instruction. These 3 bits, these are for the destination. So where do you want to write the answer? So you can do, let's say you're doing, what is this? 3 plus 7. And, oh hold on, this is not 3 plus 7, this is 3 and 7, but whatever. So this is the output. But where should it go? Should it just display on the screen? Should it go nowhere at all? So yeah, this should go into what we tell it, where we tell it to go. So this is the first bit here, means the A register. So if this is a 1, then that means write it to the A register. If this is 1, then that means write it to the M register. If this is 1, then it means write it to the D register. The mnemonic is AMD, by the way. Y'all might have heard of it. How cool is that? And you can also write to multiple registers at once. So you can do 110. So it's gonna write it to register A and M, but not D. You can write to all 3 at once too. How cool is that? So yeah. Oops, hold on. Whatever. And then the third one, the green input, is the jump input, and you can see this massive table, but let me just tell you how the jump operation is gonna work. So let me show you the program counter actually. That's what the jump is based on. I think this is the program counter, right? Or is this just like some other register stuff? I haven't seen the program. I haven't used the program counter in such a long time. Guys, do you remember when I was making this? This was such a hassle. I had to figure this out off camera, and I literally just added a monostable circuit and it started working just fine. But yeah, anyways, as you can see, every time I give it a clock signal, it increments by 1. So yeah, and then here's what I'm gonna do. So this is gonna tell the CPU which instruction to execute. So let's say I have a sign. This is gonna contain the program. Let's just write a really simple program. A equal to 3, B equal to 4, M equal to D plus A. Hold on, this is not how you write an A instruction. Let me correct it real quick. Yeah, so this is a really simple program. It has 3 steps, right? Step 1, step 2, step 3. The program counter is what's gonna count those steps. So when the program counter is at 1, it's gonna tell the CPU to do at 3. More like there's gonna be a list exactly like this, and then it's gonna tell the list to go to position 1. And then the output from the list is gonna go into the CPU. It's gonna tell the CPU to do at 3. And then the CPU is gonna be like, yeah, I've executed that instruction. So then the program counter is gonna step up. It's gonna start outputting 2. And then it's gonna go to the list. It's gonna say D equal to 4. That instruction will go to the CPU. It's gonna execute that. And yeah. And what jump will allow us to do is create loops of sorts. So if you reach, let's say you reach step 4, and step 4 says go back to 1, go to 1. So this is a really simple, really silly loop. So go to 1, this is what's gonna tell the program counter to go back to 1. So this is what the jump instruction in the end is gonna do over here. So let me just show you the entire table. So here is the table. This is what you're gonna want to look at. And I've just made some combinations here. So 0, 0, 0. Very logical. It should mean don't jump. So if these three are 0, then that means don't jump. Just continue with the next operation. If this is 0, 0, 1, then it means the code here is JGT. Jump greater than. Sorry for my bad handwriting, but whatever. So when the output of the ALU is greater than 0, then it's gonna jump. And the place where it's gonna jump, I should specify that too, is whatever stored in the this @ register. So the A register, whatever stored in the A register, it's gonna jump to that. So in the current example, you know what, let me actually make it a little better. So currently the A register has the value of 1, and if I add an unconditional jump here, JMP jump, unconditional jump, then it's gonna jump to 1 because that's literally the value of the A register, so it's gonna jump there. And yeah, here we also have some other jump statements. Jump equal to, jump greater than, equal to, jump less than, all of that good stuff. And then of course what I mentioned, the unconditional jump. So like you can use this for while loops, okay? So like you're gonna have a loop that, this is an unconditional while loop, so this is gonna be repeating in this loop forever and ever. But the actual way to break out of a loop like this is to check for a condition in between. Like let's say instead of b equal to 4, you say something like if x then go to 6 position, like this. So if x is true, then it's gonna jump to 6th position, which is gonna be beyond jump. So yeah, this is how you break out of a while loop, I think. I haven't done assembly language programming much. I did the basics, but I'm pretty sure I have a pretty certain grasp of the language. And yeah, oh yeah, this is the blue table. This is the proof of how overpowered these 6 inputs are. This is literally just an adder wearing the robe of a computer, but it's literally just an adder, and it just happens to be able to do subtraction. It just happens to be capable of doing logic stuff. The design is super elegant, and yeah, that's what gives these 6 inputs so much power. So you can just have a look at all of these things, look at how capable this ALU is. It doesn't natively support multiplication or division, but who even cares? It's a computer in Minecraft chat. World download available on Planet Minecraft, by the way. Let's go. So it can do 0 obviously, 1, -1, D, A, not D, all of this stuff. Oh yeah, of course. And it can also do A plus D, A minus D, D minus A, all that logical stuff too. That's what's gonna make this a computer. So yeah, that's the end of my notes, because that's all you need to know right now. So yeah, as you can see, it is possible. Oh yeah, and I should mention this line. This line is very important. I just glanced over it. Everywhere where I have mentioned A over here, you can also replace that with M. So in this table, wherever A is mentioned, A over here, you can just replace that with M, because, you know, I mentioned this purple thingy over here. Yeah, when it is 1, it swaps out the A for an M. Yeah. And now let's actually discuss the computer hardware, the part that hopefully you all have been waiting for. Let's switch to white, because it's a neat color. Where should I start? Should we start at the ALU? Right? So I'm gonna make the diagram first, and then I'm gonna figure out if I should use the 4-bit ALU, the 16-bit ALU, or maybe an 8-bit ALU. Now the funny thing is that I have already built 4-bit RAM. I've literally built everything around 4 bits, but I want this computer to be really capable, and 4 bits is not gonna cut it. Whatever. So, but the really neat thing about RAM is that you can literally stack all of these. So this RAM module is gonna represent the first 4 bits, and then the one on top of that can be the next 4 bits. How cool is that? And then because the ALU design is also quite elegant, you can stack this as well. That's literally how I've extended this 4-bit ALU into this 16-bit one. So yeah, without any further ado, yo, Fork Bud, new guy. Anyways, so let me draw the ALU. Should I draw it like this? Like a trapezium, or should I consider drawing it like the more conventional way? Like this looks fancy, but sadly my drawing skills are not fancy. Let's stick with the trapezium shaped ALU. I label it. And then how many inputs is it gonna have? It's gonna have this one input for the D input. Let's label it D. This one is gonna be A. I'm just gonna say AM. Who's gonna make a slash on an iPad? Not me. And then here we have the 6 control inputs. Let me actually just do I need to make all 6? I'll just make one line because it's obvious. It should be pretty much common sense. The 6 inputs are gonna be bundled together in the instructions, so I should be... In fact, there's 7 control inputs, my bad. 6, 7, same thing. Yeah. How I don't even understand, my bad. I read that wrong, but well, I'll try to make it really simple, but you know, if you are just tuning in right now, it might be a little difficult to understand, but I'm sure you'll get the hang of it real soon. And also, if I haven't mentioned already, the world is available on Planet Minecraft. All of this knowledge available at your fingertips. But yeah, you can probably also watch my showcase videos. I promise I'm gonna explain everything. This is gonna be quite concise. It's gonna be really comprehensive too. It's gonna be computer engineering level. Yeah, what type of computer am I building? Is it machine? Hold on, let me go to the YouTube app and see what... Bro, the chat is invisible. Hold on, just give me 3 seconds. I'm gonna... Yeah, I can see a message now. What type of computer are you building? Is it a machine made to solve problems? Oh yeah, this is actually quite a capable machine. Apparently you can use it to... I saw a Redstone computer on YouTube, and the guy made a program to calculate factorials. So it was literally calculating factorials on its own. You can also make it calculate prime numbers. You can make it calculate any sort of numbers. Like if you've been to a class and you've learned Java, Python, and you've made number programs, you can do that on this computer too. And apparently, if you are really smart, you can apparently code an entire operating system for this. So you can have a proper system, you can like draw lines and stuff. You can create high-level languages for this too. So you won't be stuck in assembly language turning on pixels one by one. That's a pain. But yeah, apparently you can make games like Pac-Man on this too. I won't be doing it because Redstone is extremely slow. I'm gonna stick to stuff like prime numbers, factorials. Probably matrices would be interesting. You all wanna try that? But yeah, anyways, back to where I was. Here are the 7, hold on, these are 6 control inputs. In our instruction, we are gonna have 7 control inputs, but one of them goes to a multiplexer, not to the ALU itself. So these are 6 control inputs. I don't need to write that, but I think... So our first multiplexer is actually gonna be here. I might as well draw it right now. What symbol should I use for a multiplexer? A triangle? Let me draw it correctly. Actually, my art skills are so bad. So here we have two inputs and another input to control the multiplexer. Here we have the A input. These are registers, but I'm gonna draw them as inputs right now because I don't wanna bite off more than I can chew. By the way, 7 viewers is insane. Y'all wanna say hi in the chat? So this is the let me actually number this actually. That would be smart. Let's just start from the left. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, hopefully it should enhance my writing soon, because I need enhancement. So yeah, this is the one for the 4th position? Yeah, the 3rd index, the one at the 3rd index. And essentially what it does is that it chooses between the A and the M. So I'm pretty sure I explained this, but let me go through it once again. So this is the ALU, and the second input of this is either gonna receive the value from the A register or from the M register. So yeah, actually this bit is gonna decide if we choose the A register or the M register. And how it's gonna be implemented is through this multiplexer. It sees this bit as the control selection and these two as the two inputs, and it chooses between these two. I hope that made sense. And the output goes to the ALU, of course, through this line. And then our D input, which should be quite simply connected to the register itself. So you know what, I'm gonna go ahead and draw all the registers now. I should actually make this larger, right? So that y'all can see better. Whoa, that looks good. Let me make registers with blue. Like so. This is the... what was it? The A register. A reg. And then this is the M register. I'm just gonna draw it like a register. In reality, it's gonna be whatever's coming from the RAM. Here are the 6 control inputs. Let me just write C here, cause it's gonna come directly from the input. I can use blue actually, that's what I've used here, right? Yeah, I've used blue here. I'm color coding obviously so that my brain doesn't explode. All this is quite large, I'm not even gonna lie. And then this is the magenta control input. Let me select whatever looks like magenta. C over here, I'm labeling it. This is the D register. Let me draw it in blue. D register. Okay. So then, now we have the output of the ALU. Where should it go? The ALU has one output and 2 flags. Let me draw the flags as well. One of them is gonna be telling if the output coming from the ALU is a negative number or not. So that's gonna be useful for comparison stuff, like is this number greater than this, is this number smaller. It's like you're gonna do subtraction internally, I think. And then the other flag just tells if this number is 0. So it's gonna be useful for seeing if 2 numbers are equal. And yeah, this is the actual output coming over here. I'm gonna connect it to... yeah, so here's the logic. What should it be connected to? I was wondering. The destination, whatever we choose in the destination. Let me actually connect it to a bus for now. Let me... it should go around here, kinda like this. It should be allowed to go to the D register, but not directly. there should be, I think, a multiplexer here. Maybe not a multiplexer, not directly a multiplexer, but like something based on the AND gate for sure, because in Minecraft everything is either the AND gate or OR gate basically. But yeah, this input is gonna be the D register. Let me actually see which number it is at 10th index. Okay, let me write that with red ink actually. 10. Okay, so oh my bad, this is for the D register. So I'm gonna go ahead and select connect it to A register right now. A multiplexer here. I'm gonna give a 10 over here. What about the M register? Let me connect this line to it as well. A multiplexer here. Now let's see. A, M, D, 10, 11, 12. That makes sense. Okay. Then this should be 12. Oh, my bad. 12. Oops. And then this should be 11. Okay. So now your question is, when I said that I can make operating systems, can I make Linux? Well, Linux is way above my pay grade, but I can make an extremely watered down version of Linux, I believe. Like, I don't think we can even call it Linux, but it's gonna be an operating system, alright? So I think the operating system is gonna allow us to actually support multiplication. When we write the symbol for multiplication, it's gonna do repeated addition on its own. You don't have to write a loop to do repeated addition. And then I believe you can also find some way to support division. I'm sure there's a mathematical identity of sorts for turning multiplication into division. I heard it somewhere, I just couldn't get my head over it. I think I was kind of young. Whatever. So then here are the two flags of the ALU. I'm pretty sure they go somewhere, but let me draw the rest of this first. Then I'll be able to figure it out. So far, here's what I've been able to kind of figure out. This portion, I've sketched this out. Now let's focus on the jump section, shall we? So yeah, the jump is what these flags are for. And the CPU should also give an output to the program counter, okay? So like if there's so if there's a thingy for jump if greater than, then let's say if there's a jump if equal to, so this is what it's gonna do. It's gonna take this input and this input and it's gonna subtract them, and if the answer is 0, so let's say it's this flag, the answer is 0, so then this flag turns into a 1, okay? And then we can take this 1, we can somehow feed it through some logic, and then we take the value coming from this A register, and then that's what becomes the output of the CPU. Oh, I mean that goes to the program counter, the PC, the program counter. If this flag is 1 and we actually want it to jump when the answer is equal, okay? I hope that makes sense. I think jump, I should be able to figure it out last. It's basically just brute forcing logic, it's not even gonna be that complicated. And then here we have the firstmost bit. So if it's a 1, then nothing goes to the ALU. You skip the ALU entirely. the value gets written to the A register, that's all. Let me make some logic then. I think a multiplexer like so. An AND gate should also work, but a multiplexer is quite a lot simpler, I think. Or should I make an AND gate? Yeah, let's actually make an AND gate. So here is literally whatever is coming through here. All of this. Let's call this the instruction. The I. Okay, so this is the instruction. Big I. Is big I what you also call the... Oh, my bad, I confused it with the London Eye. Whatever. But yeah. And then this other input is gonna be the first one. Let me draw it in yellow. So the first bit of the instruction. Select yellow, please. Okay. And then this leads directly into the A register. Let me actually... okay, that looks a lot better. I got an eye for attention to detail. So yeah. Oh, hold on, why have I crossed out the ALU and not uncrossed it? Let me select this, delete, there you go. And now... Okay, there's a chance that my logic is just straight up wrong and you guys can correct me. I'm pretty sure if it doesn't work in Minecraft, I should be able to correct it. But yeah, this logic is to get a sense of how it should happen. Yeah, connect these up like so. Perfect. And then now we just have to decide the logic for the jump statements. You know what? I'm gonna figure that out through Minecraft, because you can use an iPad to write notes, to brainstorm, do all that, but in the end, when you want to get your hands dirty, you should use something like Minecraft. I know the Minecraft is nice. You can literally see every single line. Like you can visually see this is a 1, this is a 1. Even the insides, this is a 1. That's a 1, 2. Very cool. So what are we doing here? This is a 4, this is a 6. This is, we are negating this, so this is -6, -1. What are we doing here? This is, oh hold on, that's a -4, -1. This is a +6. We are adding them and then we are negating the answer. So then what does it do in the end? Let me just write it on a sign temporarily. -6, -1. It's adding 4 to that, and then it's turning all of this into -1. So then this is 6 plus 1 minus 4 minus 1. What does that mean? 6 plus 1 is 7 minus 5. So this is 2. So what is this? This is... Oh, is this doing 6 minus 4? Let me actually... Oh yeah, it is doing 4 minus 6. How cool is that? Oh, and it's also negating the final answer. Oh yeah. And then this is the flag that tells if the output is negative. It's literally just the... It's literally a copy of the topmost output, but... Well, you have this flag now. And then this flag turns on when the output is 1. Let me turn it into a 1. Let me do 6 minus 6. There you go. So the output is 0, 0, 0, 0, and this is 1. So what's this doing? This is currently checking if this input is equal to this input. Right? Hopefully that makes sense. And yeah, so here's the thing with this. Here's where this gets slightly challenging. Let me discuss this with you guys, because if I jump to writing this stuff right now, I am bound to go on rambling. So let me discuss it with you. So this is one instruction, right? Suppose you have something like add 3 plus 4 to the D register, and then if that is greater than 0, then jump, okay? But then that's 2 operations for the ALU. First it's gonna do 3 plus 4, okay? You know what, let me write down the instructions so that it's easier. Do 3 plus 4, set it to D. This should happen in 1 clock cycle. If output is say equal to 0, jump. And we don't have to specify where to jump to, because this is just gonna it's just gonna jump to whatever's in the A register, okay? So remember we talked about the A register, it's literally just gonna jump there. That's another drawback of the A register. What? Why is my iPad eating battery? Why is it so hot? Chat, just give me... You can count till 10 seconds. I'm gonna put it on charging. Charger 1 connected. Just have to connect it to my PC now. I almost plugged a USB-C in the socket of USB-A. That would have fried my computer. Did that once by mistake. Anyway, so where was I? So first the ALU is gonna do 3 plus 4, okay. That's quite simple. I can literally do that right now. Let me give this a 3 over here. Let me give this a 4, which is this one. I'm gonna add them. Yep, so then it's gonna give me this answer, which seems to be 7. Perfect. And yeah, it's gonna output that. This output is gonna go to the D register through this line. It can also go to the A register, but for that, this bit would have to be a 1. And what's this bit? It's this one. So this points to the A register. So if we haven't selected the A register, as in this bit over here is a 0, then nothing would get written to the A register. Hopefully that makes sense. If the 12th bit is a 1, then it's gonna go through this AND gate into this D register, and whatever is the output of the ALU, as in 7 in our case, is gonna get written to the D register. Hopefully that was well explained, hopefully. But yeah, but then this is the hard part. Let me show you what's gonna happen now. So if is the challenge here. If the output from the ALU, as in 7, if this is equal to 0, so how do you know if it's equal to 0? Of course you have to do some logic. You have to probably get it into the ALU, I think. Oh yeah, let me show you how you can see if a value is 0. Let's say this is the input that we are seeing. So this was the thing coming out of the ALU. We fed it back into the ALU, into the first input, let's say. The second input could be anything. We are just gonna zero it out. We can ignore this input. That's what we are doing this lever for. And yeah, if this is gonna be a 0, currently this is a 7, but suppose this were a 0, then the ALU would also be outputting a 0. It should be doing 0 plus 0. It's doing 0. It's doing 7 plus 0 right now. Now if this were actually 0, and it's doing 0 plus 0, the answer is 0, and then this flag turns into 1. So yeah, now this thingy went back into the ALU. This thing was cancelled. The ALU then started outputting 0. And it also started outputting this flag as 1. Oh. Yeah, and then this one was captured. And then, yeah, it just... that made the condition true. So this is 0. So now you can tell the program counter to jump. So now it's gonna take the value from the A register and give it to the program counter. Let me go ahead and clean up my drawing again. Where would I be without an iPad, chat? How would I be explaining all of this? So yeah, this is why CPUs use a fetch and execute cycle. So every cycle is actually a 2-in-1, a package deal. But that does make it a lot more complex if I'm gonna be very honest with you. To be honest, I don't know where to start, but this is the sort of thing that I'll do off camera. I'll have to figure it out by myself. So let me think about it. The first cycle would be a fetch cycle, right? So it's essentially gonna be fetching the data from all the registers and the RAM too. The M register is actually just the RAM. I didn't want to draw the RAM, so I've just drawn the M register. But to be fair, it is a pseudo register. Keep that in mind, okay? So yeah, you know what? Let me actually do a quick recap, and then I should probably start with the homework, because there's quite a lot of homework. I want to finish the CPU in 1 week, okay? That's kind of a hard deadline for myself, but doesn't seem impossible, right? If you try, everything is possible. So let me recap for the 8 concurrent viewers. I explained this when there was 0 viewers, so I should explain this again. So yeah, I've built the logical part, the ALU. Where is it? This is the ALU, which stands for the Arithmetic and Logic Unit. It can do addition, subtraction, sorts of comparisons, negative numbers, a lot of things. This is overpowered and it's also elegant, which is what makes this special. But yeah, it has 2 inputs. The first input is where you can input one number, and then the second input is where you input the other number, and it's gonna do operations on them and give an output. But like, what do you do with these outputs? You're not making a calculator, are you? You're making a computer. It's supposed to do thousands of calculations per second, ideally. So yeah, where do the numbers come from? Where do the numbers go? They go to registers. So let's talk about the first register. It's the D register, which stands for the data register. And you know, it's actually a really simple register. It's like a variable that you create in programming. So like Python programming, Java, C, whatever you're learning, you've surely used a variable before. So like variable X, you can do X equal to 3 plus 4, whatever. In this case, that's the D register. I forget my iPad can do math by itself, but that's cool. So yeah, examples are D equal to 21. Really simple. You can also use other variables as the inputs. So the other registers, I mean. So D equal to A plus M. That's also one thing you can do. Speaking of the A register is the address register. And you know, this is actually basically the same as a data register, except it has some side effects. So yeah, it's like you create a variable Y, except it has a side effect. And what the side effect is that it selects an address in the RAM. Let me show you the RAM right now. So this is the 256-bit RAM. It has 256 bits of storage, which are bundled together in chunks of 4, which is called a nibble, like a small byte. I did not name that. But yeah, it has 6 address inputs, 1, 2, 3, 4, 5, 6. Using these 6 inputs, you can select any register from this RAM. But yeah, so whatever is the A value in the A register, that's also gonna go to the RAM as the address. So let's say you have 100 written in the A register, and by the way, the syntax to write something to the A register is not this. You don't just say A equal to 100. Instead, this is what you have to do. @ symbol, @100. Oh, 100. 100. Yeah, this is a little bit simpler than doing A equal to 100, but like it's a little counterintuitive, okay. So let's say you've done A equal to 100. So then it not only stores 100 to the A register, acting like the data, but it also starts sending 100 over here. So this gets sent to 100 and it chooses the 100th register over here. Now sadly this only has like 64 registers, but whatever, just continue with me for this example. So yeah, and also of course you can also use other variables as the inputs like this. And then we have the M register, which actually is a pseudo register. This is an important thing to keep in mind. The M register is a pseudo register. So in circuit diagrams you can draw it like a register, like let me show you. This is perfectly acceptable in a circuit diagram. In a real computer, this register doesn't exist. So like when I'll be building it, I won't actually build the M register. But yeah, what it does is that it takes the value in the A register, feeds it to the RAM, and whatever comes out is the value of the M register. So you can see that the M register is kind of dependent on the A register. So yeah, the output coming from the RAM is the value of the A register. That's kind of elegant if you think about it, cause then you can use the symbol M in programming, which is really important. You can use the symbol M to refer to whatever is the output from the RAM. Okay, I'll just recap on the instruction too. Oh yeah, these were the 3 registers that will be present in the CPU. I think they're kind of simple. And then other than that, here we have the actual instruction, the instruction itself. So like in Java you can have something like x equal to 3 plus 4, but not here. You have to actually write stuff in binary, because that's the only thing the computer understands. You can't say add this to this. You can't treat it like ChatGPT, obviously. What's wrong with the battery? Whatever. So let's just start with the first bit. Okay, that seems simple. Here I've written the description, but essentially if it's a 1, then if the instruction is something like this, @A30, so then this bit becomes a 1, and what it tells is that this is actually a number that I want to save into the A register, right? So 30 would be what would it be? 16 plus 14, so that would be whatever, you'll get it. But then if this is 0, this bit is 0, like so, then that means that the rest of it is an instruction. And actually for an instruction you can ignore these two, they don't really have a purpose. So then let's start with the third bit. What does it do? The bit at third index, I mean. So as I said, this input can be either this input can receive either the value from the A register or from the M register. And essentially this bit allows us to choose either A register or the M register. So yeah, if this is a 1, then we'll be giving this input the value coming from the M register, otherwise we'll give it 1, the value from A register. And then these 6 inputs are literally just the control inputs. So whatever we write here, let's say 1 0 1 0 1 1. So then this is what we'll give to these control inputs: 1 0 1 0 1 1. So it should do some meaningful operation. Let's see what it's doing. It's zeroing this, it's zeroing this as well. It's adding them, and then it's negating the answer. What? So it's gonna give 1 1 1 1. Sure, it does. But yeah, and then here in red, these are the destinations, so it allows us to select where to write the answer. So obviously this ALU gives an output too, right? And where should this output go? You can't just write it in some memory and forget about it. You can't directly display it on the screen either. So then these 3 bits allow us to select where it gets written. If this is a 1, it gets written to the A register. If this is a 1, it gets written to the M register. If this is a 1, it gets written to the D register. And you can also write to multiple registers, like this writes to A and M, and then this writes to A and M and D. Oh, why is it trying to solve stuff for me? Yeah, and then here in green we have the jumps. So you can see all this really cool stuff, and let me actually tell you the purpose of jumps. So we have a program counter, right? And yeah, the program counter, let me actually give you a sort of demo. Let me write a really simple, let me actually write it on the iPad itself. That's just superior. So let's say we have a really simple program. We write 1 to the A register. We do D equal to A plus 3 maybe. Then we do D equal to D plus 1. Sure. And then here, let's say we do something like if D is greater than 0, then jump. So now you might be wondering, where is it gonna jump? Is it gonna jump on the spot? It's actually gonna jump to 1, because that's the value in the A register. It's gonna jump to whatever is written in the A register. In this case, it just so happens that 1 is written in the A register. In reality, before jump instructions, you're gonna make sure that whatever is written to the A register is where you actually want to jump. So yeah, this is a really basic example. You can ignore it. But yeah, what was I saying? So yeah, this is the purpose of the jump instructions. And then you can just refer to this table. It's kind of arbitrary, but let me explain the most important ones. 0, 0, 0. So if these ones, all 3 of these are 0, then it means do nothing. Just continue with the code. Execute the next instruction like nothing ever happened. So then do this, then do this, then do this, then do this, because these do not have any jump statement written with them. No jump is mentioned here. So yeah, it's gonna continue execution of the code. And then here we have jump if greater than. This is a J, this is a G, this is a T. Pardon me for my sloppy handwriting. But yeah, if the output coming from the ALU, this is the ALU, this is the output coming from the ALU, if this is greater than 0, then it's gonna jump to whatever is written in the A register. It's gonna tell the program counter to go there. And yeah, it's gonna execute whatever instruction is written there. And then here we have some other stuff. Jump equal to, jump greater than equal to, jump less than, all that good stuff. And then here we have an unconditional jump. So you can use it to create while loops, like a while true loop. It's gonna keep looping. And let me show you this cool thing. The way you jump out of a while loop is that you have a, let's say you have something like add 1 here, you have instructions here, more instructions, a lot of instructions, and then you have an unconditional jump. So it's gonna jump to 1. What you're gonna do here is that you essentially want to execute all of these over and over until something is true. Basically, you can write it here. So if x go to let's say 100, let's say this is at position 80, and then 100 is gonna be here. So it's gonna execute all of these, go to jump, go back to 1. But then if this condition happens to be true, if x happens to be true, then it's gonna go to 100, which is over here. It's gonna bypass this jump statement like it never happened. So yeah, so this is the purpose of an unconditional jump. It's quite powered, or quite overpowered, like everything in this PC basically. So yeah, you know what, I was thinking of ending the stream, but I have 10 viewers, I might as well continue, cause y'all are watching. Let's go. So let's do the first things first, connecting the ALU with all its inputs. You know what, why don't I make a 16-bit CPU? How hard could that be, right? Let me think this through. So let me scribble some stuff again. What's the largest number that an 8-bit register can hold? Let's do 4-bit first. 4 bits. So 2, 4, 8, 16. 2 to the power 4 is 16. So it has 16 possible combinations. 7 of them will go to positive numbers, 8 of them will go to negative numbers. That's just how 2's complement works. 2's complement is really elegant, so I'm gonna stick with using that, obviously. Let me write what? 7 to minus 8. 7 to minus 8. Let me actually write it in this form. And then with 8 bits, let's do oh what? 8 bits? What's it gonna solve? I don't know. So yeah, with 8 bits we get 2, 4, 8, 16, 2, 4, 8, 16, 32, 64, 128, 256. 256 possible combinations. 127 of them will go to positive numbers and 128 will go to negative numbers. That's just how 2's complement works. And then a 16-bit CPU. Hopefully I don't mess this calculation up. 2, 4, 8, 16, 32, 64, 128, 256, 512. I lost track. Oh, hold on, let's try solving this. What's it? Okay, 16 bits is 2 bytes. Well, thanks iPad. I mean, it is helpful when it is helpful. Let me just use a calculator. I'm gonna lose track. Let me show you my calculator as well. 2 to the power 16. What? 2? Oh. Well, this is underwhelming. How do I do 2 into 2? This is 2 to the power 2 to the power 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so it can do it has 65,000 this many combinations. Let me divide that by 2. So this -1 for positive numbers. 32767, 32k. The OGs know what this number means. 2 minus 32768. Alright. Chat, any 2B2T fans here? Or in fact any Anarchy server? Y'all would know what a 32k is. So yeah, I mean, getting back to the point, 16 bits is definitely more powerful than 8 bits, but like 32,000 numbers, do you really need Minecraft to be that powerful? Keep in mind that it's gonna more than double the lag. So over here you have, over there you have a 4-bit ALU, which is elegant. You do something and it finds the answer. Let me do, you know what, I should do 1 plus all ones. Let me show you the answer happens one by one, I think. What am I doing? This is 1111. All ones, yeah, there you go, that's what I'm talking about. And then you add 1 here. There you go, they all go off one by one. Because I know carry cancel addition exists. I remember watching a video documenting it, but like, to be honest, I mean, I'm a computer science guy, I'm not a Minecraft tech sort of guy, if you know what I mean. So I didn't pay much attention to it, I just use what computer engineering uses. So yeah, this is slower, as you can see. And yeah, this delay adds up when you have multiple ALUs stacked on top of each other. Let me do the exact same thing here as well. Adding them. No need to negate the answer. Look at this. Oh, what? Nothing? All ones over here. They're being... and oh. Okay, now look at this. All these lamps are gonna turn off one after the other. That is a significant amount of delay. The only way I can compensate for it is... by reducing the clock speed. So, okay, I can see part of your comment. Let me just... yeah, I can see your entire comment now. So you're from Brazil and you wanted to know what architecture my CPU has. Well, I mean, you might be expecting something like x86 or ARM, but to be honest, I don't really have a name for this sort of architecture. How do I say it? It's kind of just a custom build. If you want to search up where I got the inspiration for this, it's called a hack instruction set, I believe. Let me just search it up. Hack instruction set, I think. Hack computer. Oh, there's an entire Wikipedia page about the hack computer. Oh yeah, this is basically what I'm building, the hack computer. HACK. Let me write it in chat as well. Why is the chat not working? Let me use my... so I'm using a phone to preview my stream. And it just happens to be signed in from the other account. So I'm just gonna say hack computer from that. So yeah, I feel like, honestly, I feel like the 16-bit is kind of overkill. So, okay, but I'm gonna be honest, 127 being the maximum number that my CPU can process. I mean, imagine this, you are buying a laptop and it only has 16 gigabytes of RAM. That might seem like a lot, but you want to future-proof, right? So you would prefer to go with 24 32 GB of RAM. Not because you are sure you will need it, but because you want to future-proof. That's the exact dilemma I am in. So 8 bits would be faster, would be simpler, would be, I don't know, better probably, more elegant for sure, but then 16 bits. Chat, why don't you advise me? Why don't you advise me in the chat? Should I build the computer to support 8-bit numbers or 16-bit numbers? Do keep in mind that my streams can be a tad bit longer if I build the 16-bit computer, because there's more stuff to debug, more lines to build. Let me show you the complexity that comes with the 16-bit computer. So this is the glass tower. Let me show you what it's supposed to actually be. This is a glass tower. You can see the signal strength from the bottom travels all the way to the top. Nothing wrong with that, right? It's perfect, how it should be. But over here, why do I keep setting it to night? You can see that the signal from the bottom won't actually reach the top. That's why we have repeaters here. Repeaters repeating the signal. If I just remove this and I give this a 1, you can see the glass tower continues all the way till the top, but the signal does not. It's on right here, but it turns off. So a repeater here, and now the signal travels perfectly well. So chat, y'all are supposed to tell me if I should build a 8-bit computer or a 16-bit computer. I have taken a look at the advantages and disadvantages. So now y'all tell me. I'm literally bamboozled, because 8-bit computer is impressive, but 16-bit computer is more impressive. But like, it's diminishing returns, if you know what I mean. Also, in the preview of the stream, I can see this green box, and it only comes for like 10 seconds. When my iPad turns off, I have no idea what the purpose of it is. You know what? Should I ask? Oh, let me actually ask on the FixoGenie Discord server. Why don't I invite you guys to the FixoGenie Discord server? That would be cool if y'all wanna join. Completely optional, by the way. Let me invite. I'm gonna... Why can't I just create an invite? I'm turning into a boomer, chat. I'm a Gen Z, but I'm turning into a boomer. Okay, use the invite link. Oh, chat doesn't work. That sucks. I'm just gonna ask in the central. Should I build a 16-bit computer or 8-bit computer? Oh, green box, let me get rid of it manually. I'm just gonna ping everyone here. I'll be a menace, pinging everyone on the Discord server. Oh, in Minecraft. Okay. Okay, yes. Yes, I'm sure I want to ping 30 plus people.
Double O Win said Double O Win said
I have narrator enabled, I forgot. Okay. But Double O Win is quite the goat. Shout out Double O Win. Alright. Double O Win says 16-bit. Thank you. Alright, so yeah, so I'm gonna build the 16-bit computer now. I have a 16-bit ALU kind of ready. I only have to implement the flags to it, right? let's see. So this flag should be, well, extremely simple to implement. How have I done it here? So I've placed the lamps on top of the target blocks. Oh yeah, that makes sense because like I can't get the signal from here. I want to get this signal. This is the output that I'm trying to hijack. I could place a comparator, a target block there. Repeater here. Like, why increase the complexity, you know? If you have something that works, then use it, right? What am I doing? Okay, all the output lamps have been repositioned. Alright, let me go back to the top. Hopefully I don't miss the throw. Perfect. I'm basically infamous for missing pearl throws. Should play Yara Fong with Tom Pearl. That's the pearl throw. Oh, bad joke. Okay, so this is our flag. This tells us when the output is negative. And it seems like it's working just fine. I guess now I need to have a glass tower. And I'm pretty sure I'm gonna need either repeaters or torches here. So when all of these are zeros, the output should be a 1. So that means, hold on, if any of this is a 1, then the output should be 0. So we are gonna do an OR gate and then we are gonna NOT its output. Makes sense. Okay, so that means I'm gonna have to place repeaters here then. Where should I place the repeaters? Should I just place the repeaters facing the target blocks or next to the target blocks? Let's just see what I've done here. I don't want to run into last minute problems. Okay, I've placed the repeaters here. Glass tower there. Makes sense. Not very good from a packaging. You know what? I'm just gonna try this way. Since my previous design wasn't perfect, I feel like I can do better from a packaging standpoint. Right? Packaging is important too. Packaging is underrated. It's the reason why... Okay, I was gonna say why the Dodge Challenger V8 isn't available in all-wheel drive. Niche things. Anyways, now I'm gonna place a repeater here. How efficient can I make it? There's gonna be a bunch of lag, so I better make it efficient, right? I don't know. No. Oh, this doesn't. Oh, except if this line is a 1, it's gonna power this lamp. Oh, hold on, wait a minute. This is one thing that I have not considered yet. These target blocks are literally the output of this thing. I can't be building something in front of the output itself. Get rid of everything. So does that mean that my design that I've glazed for so long is not perfect? Well, it isn't. Nothing wrong in admitting that. Alright, so where should I place the glass tower then? If not there, I'm thinking I can place repeaters here. This seems like a pretty good place to place repeaters. Kinda like this. Alright. Repeaters. This is kind of a monotonous task, but I don't know. I find it fun because there's also music. Speaking of music, how do y'all like the music? This is music from Epidemic Sound, not sponsored, but I'll happily share my affiliate link. Anyways, I'm gonna build the glass tower here. Have y'all heard this music in Ryan Trehan or Carves video? Actually, if I'm thinking about this, you know what, I'm just gonna build a normal looking glass tower. I don't have to be all hyper focused about efficiency, because at the end of the day, a clock that's like 0.01 hertz faster, how does it even matter? Less than that, much less than that, the clock is gonna be like 0.01 hertz at its fastest when overclocked. I don't know. Oh, how tall is this glass tower, bro? This felt like building the Burj Khalifa, bro. The 16-bit ALU is kind of tall, especially when the adder was designed by me. Look at how inefficient this is. Oh, remember that one random hate comment by that kid who went like, stop pasting in the schematics, build it in survival. Yeah, literally look at how inefficient my design is. But like, it's all designed 100% by me. What other proof do you need that the average human is smart? Like, I'm trying to prove a point here, just let me prove the point, little bro. Anyways, where was I? So 0, all of this, 0, this 2 maybe. There you go. All of this is 0 now. Oh wait, the bottom one should be 1. Let me just write a 1 to it manually. This is a 1. Don't see it. Add these maybe. Why is this not a 1 yet? What am I doing? I'm adding... Oh, my bad. There you go. Okay, so this glass tower is receiving a signal from here. The signal is traveling here. So can I place a repeater here? That would be more efficient, but like, I don't know. I'm just gonna stick with the more efficient option, because that probably means I might... If I choose the less efficient option and then I'm like, I should have chosen the more efficient option, that's a possible point of regret, so I might as well not. Alright, hopefully the glass tower should be connected. By the way, chat, have you all watched the most recent Spider-Man movie? The Brand New Day? How was the movie, chat? No, what? I need to place a repeater here because this one output isn't connected. Some workaround maybe? No, I don't think so. Or maybe I could allow the signal to travel down onto that. Is that valid? How though? I want the signal up here to go down. You know what? I'm gonna make this easy to understand, because at the end of the day, this computer, who's gonna use this computer? It's a learning opportunity, so I should make it simple to understand, even if it means increasing the delay by a tiny bit and making the perfectionist inside of me extremely angry. Whatever. What color should the flags be? You know what? Everything is turning yellow here for some reason. To be fair, address lines are quite important. Oops, I broke the signs too. I was not intending to do that. 0 dx, and then negate the X. This is what this input does. The control inputs, I think they should be blue. Because, let me show you the diagram as well. Here is the diagram for the... How did I scroll so fast? I did not mean to show the Among Us, but shout out to the Among Us. Okay, where was I? So, these 6 are literally what's gonna go into the ALU. Right, I've said this 4 times, I think, because it's just that important. Okay, and then now what? Let's go back up. And yeah, I think is that both the flags connected? No, I need to place a torch here. Any better place to place the torch? By any chance? Here maybe? Ooh, perfect. It's in line with this display and this output too. Hold on. This could... I might as well use this as the flag. Get rid of this unnecessary stuff. Okay, I'm using glass here as the bounding boxes, but seems like it isn't inaccurate. Whatever. So yeah, this is the flag. Oh, oops. So this flag is getting connected to this glass line. That's unintentional. I'm gonna get rid of this for like the 20th time, and I'm gonna rebuild what I had. What works, and what works is not to be messed with. That's a very important rule in the world of redstone, even in the world of cars, I guess. Okay, yeah, this is the flag. Let me test it out. If I turn that off, then this lamp should turn on as well. How do I turn it off? Like so should be simple. And is it? Yes, it is on. How simple is that? So yeah, I think that's the 16-bit ALU done. I can't believe I'm using a 16-bit ALU. Double Oven is such a goat. He just told me to build a 16-bit ALU. I can't believe it. Oh wow, my best friend joined the server. I don't remember inviting him. Let's go. Glad you're here. Yes, 16-bit, let's go. Anyways. Okay. What is that? That's the... Oh wow. I remember building this. I remember designing this. This took way too long. This took... Yeah, this is the design for the adder itself, which I glaze and demolish at the same time. But yeah, that's the ALU done. What else is there to be messed with? Oh, RAM. I could literally just copy RAM on top of the other. Let me go here. Alright. Oh, by the way, I'm gonna use schematic mods. If you're not a noob, you're gonna know that I only make schematics of my own stuff. I don't paste schematics from the internet. And I can prove it. If you guys can find sufficient proof that I pasted a schematic from the internet, you get Discord Nitro, no questions asked. Moral of the story, don't be a stupid noob. I'm just flaming that one comment. I should put him on the screen. The pin of lame. You know what? That's how... I'm not gonna be boring. Let me show you. This guy. Oh. Oh, I thought I cut out his name, but apparently I did not. I'm just flaming him. Oops, I clicked onto the screen. No, and now this got unselected. Oops. Whatever. I can select it again. The first point is here. Oh, by the way, this command block here, this serves no purpose. It was to clone the thing. So you can see I was cloning it layer by layer. Yeah, I can get rid of it now. Now let me select these purple lines as well. And then let me go to the other side. Make sure everything is selected. Oh, this portion isn't selected. I'm glad I checked. How did I miss this? The bounding boxes aren't even accurate. What? Get rid of this. Okay. Yeah, I think... Did I see a chicken in my build? How did a chicken spawn in here? I don't know. Okay. The menu top 2 tries to open. And I'm sure I did not click the wrong key. 256 bits of RAM. Hold on, do I not have the schematic for the saved already? I must have a schematic for the saved. Hold on, have I made sure that this works? I'm gonna go ahead and save it, because like I might have it saved, but it's not in my brain's RAM, okay? My brain's memory doesn't remember building it in the same detail that I actually built it in, if you know what I mean. So a refresher would be nice. 256-bit DRAM. I should make the distinction from VRAM. Because here's the concept. This DRAM only outputs the currently selected register, whereas the VRAM, it sequentially outputs everything serially. But yeah, it serially outputs the value from every single register after register, one register after the other, onto those blue lines that you see over there. Yeah. This is only gonna output the value of the currently selected register, and that's important for DRAM, okay? Because you remember that M register, the pseudo register, which was actually just the value of the RAM? Yeah, that can only have one value. It might sound obvious, but well. So anyways, I think I'm gonna go ahead and place the DRAM right around here. Maybe. Seems about right. Let me align it perfectly. Okay, I should place it onto this block. If I load the schematic right now, 256-bit DRAM, maybe I'll see it. Oh, working 256-bit DRAM. Load schematic, it has been loaded. Be prepared to see some lag. Oh, not that much lag. Okay. I think I should just be able to paste it in. Let me make sure that it's actually at the exact same level. Because as I said, I'm a perfectionist when it comes to redstone. And basically everything, honestly. I guess I'll paste it in. What was the keybind again? Oh, done. M plus P. I guess I'll go ahead and paste it in on top of this too. right? Oh, so much overlap. Oh, no, this is too much overlap, I think. Oh, yeah, this is cutting the lines and all that. Move this up one block. Now there is overlap, but it's like it's trying to say that this stuff is supposed to be air, I think. What does the schematic say? This is schematic says this should be air. Oh yeah, schematic says this is supposed to be air, but like, what if it's some other block? How does it matter? Okay. I think that should be fine now. Yeah, let's go ahead and paste it in. So chat, I don't remember very well if I clarified this. I'll just re-clarify it just in case. So these are 4-bit RAM modules, so they can store 4-bit numbers. Like we have 8-bit numbers, we also have 4-bit numbers. 8 bits is called a byte and 4 bits is called a nibble, like a small byte. I have no idea who came up with this language, but I think it's cute. Also a little cringe, but I'll accept it. So yeah, the really cool thing that we can do here is actually chain these RAM modules. So here we have 4 bits, here we have another 4 bits. We can say you wanna write 0001 0011, and that's an 8-bit number, but you can split it across these 2 RAM modules and then write it like so. And yeah, that's possible too. Just be sure to give the same addresses here and connect all the inputs together. That way it just becomes one large piece of RAM. Hopefully. I mean that's how the logic works, right? I could be wrong, but the only way to know is to try, right? Oh, this is way too much overlap. This should be fine. What is this? Red concrete. Why do I not have this red concrete on the layer below? Oh, I have it? I did not notice it. Okay, so it does have one layer of overlap. I'm gonna go ahead and paste it in anyways. I just have to load the schematic one more time now. Right about here. Oh, a little below, but I'll just move it down. Absolutely no problem. One layer of overlap. Paste it in, and I can just go ahead and remove the schematics. Oh, I've pasted this in right. Hopefully right. Have I pasted it in correctly? Have I misaligned something? Let's see. So the lever should be above the lever. It is. Let me get rid of this then. Okay, I guess I'll just go ahead and connect up all the inputs then. And you know what? I'm not gonna be building the glass columns manually for like 20 more minutes. I'm just gonna steal them from the other build that I made. Stealing from myself is a cool concept. I wonder why people think it's bad to steal from yourself. What's the ethical implication of stealing from yourself, chat? Anyone ever thought about all this? Oh, what? Okay, so only the third iteration of this thing lacks a program counter. What? Is there something over there too? Far off? I swear I saw something. Nothing. Whatever. I did not mean to use the Riptide 10 trident twice, but whatever. So all the glass towers should be present in approximately this area. I guess I can just select the entire... Oh. This one also has the concept for these. This one also has these 2 additional address lines. So it's gonna allow us to select among these registers. Oh, hold on, but all it does is modify the load signal, right? If I just get rid of these green lines and instead move this glass tower a little bit, I should be good, right? We'll see. One way to find out. That's to actually go ahead and do stuff. What? Why do I still have the program counter in here? This program counter serves absolutely no purpose. I don't even think it's connected to anything. Look, it's connected to these lines, which is connected to this torch too. This circuit, which is disconnected from anything. So I can get rid of this program counter. Anyways, where was I? So I was supposed to select these glass columns, right? But if I click in the sky, nothing. Oops, I messed that up. Okay, so I don't have to connect all of the inputs to the exact same value, right? Oh yeah, I don't have to connect all the inputs to the same value. All I have to do is connect all the outputs. What? Why is this? What are these doing? I do not know. I fail to understand how I can be stupid and smart at the same time. I mean, it's hard to believe that... How do I say it? It is kind of a smart thing to be building a computer in Minecraft, but it's just so unbelievable that I'm doing it. Okay. So here's what I have to do. Move this a little inwards. I think hopefully that selects every block, or not every block yet. Nothing wrong in selecting extra blocks, right? Okay, I'm just gonna go ahead and save the schematic. Temp glass towers for 256-bit. Oh, hold on, this is like 1024-bit DRAM. Perfect. Then I'm gonna go head back to that. There you go. What? Why does it render farther than... Objects are closer than they appear. Just like the text in the rear view mirrors. Why am I making so many car analogies today? Chat, should I make a car channel? If I made a car channel, would y'all watch? But... where should I load it? Here maybe? Oh, by the way, how many of y'all are watching on... Which devices are you guys watching on? I heard 25% of people watch on the TV, which is just completely unbelievable to me. Not like it's wrong or anything, I mean, watch on the Samsung smart fridge if you want. But like, I never imagined this. I never imagined that someone would watch me on a TV. So are y'all watching on... what sort of devices are you watching this on? I'm guessing most of y'all are watching on TV because the chat is so dead. do I place this now? That is the question. Am I placing it one block too high? Seems like it. Oh, I'm placing it very wrong. I was placing it way too wrong. No. Okay, that's better. I think. Like so. That should work, I think. Okay, so this mod does not override the current block, so I think I should break these first, I think. What does this mean? If I just go ahead and break everything, the mod is just gonna do everything by itself, I think. I do not need to be breaking glass, but whatever. Okay. Oh, is it gonna create floating dust? Floating dust? What? Hopefully it does. That's gonna be hilarious. Anyways, without any more delay, let's go. It actually created floating dust. No. What happens if I power it? Is it actually gonna power anything? So to power it, I'll have to power this block. Oh, can the dust break if it receives a signal up? Wow, I updated everything. What? Yeah, I gave this dust a signal update. So then this dust vanished and updated this dust and updated this dust. Oopsies. Well, it was gonna vanish either ways. Can I power anything using this? Oh, will placing a lamp here update this? Not yet? Wow. Anyways, why am I... What? More floating dust? No. Oh, placing a block below it did nothing. Okay. Actually, I'm pretty sure I kind of took a wrong schematic of it. So I missed the... What? Uber parcel? It's 1:30 AM. Why is Uber parcel coming? Chat, this might be... Give me 30 seconds. Uber parcel is not supposed to arrive at 1:30 AM. I'm not approving it. Chat, has this ever happened to you? Y'all DoorDash at 1:30 AM? Okay, I'm gonna get back to streaming. Uber parcel, I don't know. Y'all guys. Uber parcel can come again, I don't know. Thief won't come again, luckily. Alright, so... Where was I? You know what, let me actually... Since my flow has been broken anyways, I might as well go see what I was doing there. How did I actually connect up those things? Look at how fast this is. Wow. Oops. Okay. So I'm pretty sure I'm missing a layer over here. Oh, I'm missing a lot over here. So these repeaters are powering these. What about these address lines? How are they receiving power? Oh, nothing? Seems like nothing is powering these address lines. Where am Yeah, these address lines are completely disconnected. What about the load signal? You know what, chat? I think I should be able to figure something out. I mean, to be honest, it looks simple when you're looking at the finished thing, but when you want to do it yourself, it's a lot harder. What? Okay, what if I just paste the schematic like so? That should fix these floating dusts. What's in here? Wrong state? Yeah, I think that's what orange means. Why is the state of this wrong? Cause... What? 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 Yeah, this mod can do stuff like this. How is that? How is this torch burning out? Which torch just burned out? What? How is... Oh! No, 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 no. Where is the torch? Which torch is burning this out? Keep in mind this is the load bit, so... What? It's in the wrong state again? Oh, I know exactly what's happening. The funny thing is that... So this line is connected to this line. I'm just gonna get rid of this green line. Wait a minute. What purpose does this green line have? Other than connecting to the wrong input at the... Oh no, Okay, I think I can get rid of this too. What? What is what connected to? Chat, you know what this is? How's the music, by the way, chat? Are y'all liking the song? This is, I think, Moving to Miami by Lexica. Let's see, fun. Oh, this is Press X Twice by Lexica, my bad. Same thing though. How's the music? Oh, by the way, would y'all like to join my Discord server? The double O win, the absolute goat, the legend, the guy who recommended I make the computer 64-bit. Yeah, this is the Discord server where I asked him. So, yeah, I mean, what else is there for me to do? This is not very advanced stuff. This is the sort of stuff that, you know, you can get a beginner, a noob redstoner who just knows. Why can I hear myself? Because I'm playing my own stream, I'm smart. So yeah, you could just get a noob redstoner, like someone who's been doing redstone for a week or so, and then he could debug this sort of stuff. This is not worth streaming, so you know what, chat, it's almost 2 AM here. I'm gonna go sleep now, and then I'm gonna do this for my homework. Now I'm gonna do the outro. So everything here, literally every single thing in this world that you see is 100% designed by me. I did not download any schematics, I did not look up any circuit diagrams. Literally everything is my own design, and the world is also available on Planet Minecraft, by the way. You can download it and see. You can mess around with the stuff for yourself. How cool is that? And yeah, so this was day 17 of building a computer in Minecraft. Please subscribe because I really want to do these streams a lot more often, and I would appreciate if you could subscribe, like the video, and check out my other channel, my other videos too, because I make other videos too. So yeah, on that note, I'll see you later, genies.